Magnetic Materials Assignment Help. Visit https://www.eduassignmenthelp.com. Email info@eduassignmenthelp.com. Call us at +1 678 648 4277. 1. Solve for the magnetization versus field for a thin film of amorphous iron-boron silicon. Assume ohms equals 1.6 T and K equals 0, with the field applied normal to the film surface. B. A single crystal sphere of Ni with the field applied along the 111 direction. 2. Does the energy required for complete saturation in the Stoner-Wolfarth model as described by EQ 9.13 diverge for 0 theta pi/2 or take on a finite value? 3. Consider the magnetization process in a single-domain particle having cubic anisotropy using a field applied along an easy axis orthogonal to the initial magnetization. Because of the uniqueness of this initial condition, i.e. the special way the sample is prepared before application of the measuring field, the result you derive will not be typical for cyclic magnetization. Write and plot the energy density versus theta, then find the shape of the MH curve. Locate the critical parameters by combining the equilibrium condition with the condition that the solution to f, theta, equals 0 also be an inflection point. 4. Consider the two-dimensional magnetization of a thin film with fourfold in-plane anisotropy Fa equals K1 cos 2 theta with an external field and stress sigma xx applied collinearly as shown below. eduassignmenthelp.com. Solve for the equation of magnetization and sketch the results for B1x0 and 0. Compare with the results in Prob. 9.4. 5. Consider a thin film with in-plane cubic anisotropy K1 and a superimposed uniaxial anisotropy with easy axis along one of the fourfold easy axes. A field is applied in plane, perpendicular to the uniaxial easy axis. A. Write the expression for the free energy. B. Sketch the energy surfaces for the various terms. C. Write the equation of motion and sketch m versus h. D. How does mh differ for Q5K1 or Q5K1? 6. Work out the steps to derive the field dependence of magnetization m, h, for a material with uniaxial magnetic anisotropy and h applied perpendicular to the easy direction of magnetization. eduassignmenthelp.com. 7. Explain why the coercivity of amorphous alloys goes through a minimum as the magnetostriction constant lambda s goes through 0. Give formulas to support your explanation. 8. Derive an expression for rotational permeability in cubic anisotropy, and compare with EQ 9.8 for uniaxial anisotropy. 9. Determine the g-factor of the YIG sphere in figure 9.46 using EQ 9.15. eduassignmenthelp.com. 1a. For each surface of the film, magstat equals 1/2 m equals ms cos, so magstat equals m. Fmagstat equals OMS. Magstat F equals OMSH cos plus O/2 ms2 cos 2 theta del F/del theta equals 0 gives H equals ms cos equals m, after division by sin, which is 0 only at and above saturation. Thus, H/ms equals m/ms equals m. The system saturates when H equals ms equals 1.27 ma/m or when B equals bs equals 1.6 tb, 111, is the easy axis, so the only anisotropy is shape. Answer is same as A. But Ha equals magstat equals nm with n equals 1/3 instead of 1. M equals 3H/ms saturation is achieved at 1/3, ohms is almost equal to 0.2 T. 2. Putting m equals 1 in EQ 9.13 gives sin 2 theta equals 0, which can only be satisfied for theta equals 0 or pi/2. So the m, h, curves in figure 9.3 never reach m equals 1 except for the two limiting cases, for theta equals 0 or pi/2. eduassignmenthelp.com. 3. The energy density, F equals K1 sin 2 theta cos 2 theta msh cos is plotted below. F is minimized for the equation of motion, m2 cubic meters, h equals 0, where h equals msh/2k1. This cubic equation may have up to 3 different solutions. The physically meaningful ones can be discerned by considering the energy as a function of theta. The equilibrium orientation theta omicron decreases towards 0, i.e. m equals cos increases as h increases. At a field h is almost equal to 0.25, the energy minimum near theta equals 1.2 vanishes and the magnetization may jump abruptly to theta equals 0, m equals 1. The calculated form of m versus h is shown. The discontinuous change in m is a first-order transition. It corresponds to what is called a switching field. It can be determined from the derivatives of the equation of motion, either del h/del m equals 0 or del m/del h equals infinity. Thus, the critical magnetization at switching is given by 1/6 mc2 is equal to 0. Thus mc equals 0.408. Or theta c equals 66.0, which occurs for hc equals 2/3 square root 6 equals 0.272. Fig. 4 Sol. 9.3, left, normalized energy density as a function of theta, radians, for different values of reduced field, h equals h/ha. Shift in equilibrium orientation with h is indicated. Right, calculated mh behavior, m increases with increasing h, then at mc equals 0.408, jumps to m equals 1.0. The dashed line in the mh curve shows the continuation of the mathematical solution. Note that the initial slope del m/del h, O equals 1 or del m/del h equals ms/ha gives the value for the anisotropy field ha. Thus, the value of K1 can be determined by measuring m, h, and using either the initial slope or the critical field hc. eduassignmenthelp.com. Prob 3. Left, normalized energy density as a function of theta, radians, for different values of reduced field, h equals h/h1. Shift in equilibrium orientation with h is indicated. Right, calculated mh behavior, m increases with increasing h, then jumps to m equals 1.0 at mc equals 0.408. 4. The energy density is F equals misbo cos plus K1 cos 2 theta plus B1x, cos 2 theta upsilon sin 2 theta, del F/del theta equals 0 gives m, 8K1, 2 square meters 1, plus 2B1x, 1 plus upsilon equals misbo where m equals cos and 1 m2 equals sin 2 theta. For x equals 0, this gives the result sketched as the solid line, Mr equals 1/square root 2, saturation, m equals 1, occurs at h equals 8K1/ms equals ha. eduassignmenthelp.com. For B1x0, Mr 1/square root 2 B1x0, Mr 1/square root 2, and ha equals 8K1 plus 2B1x, 1 plus upsilon, /s. Thus, saturation occurs at higher fields for B1x0 and lower fields for B1x0. 5a. From EQ 6.6, setting theta equals 90, we have F equals Q sin 2 phi plus K1/4 sin 2 phi minus omicron ms sin. B. Energy surfaces. eduassignmenthelp.com. C. 0 torque gives 2K sin cos plus K1 sin 2 phi cos 2 phi equals omicron ms eta cos. Divide by cos u phi, which is 0 only at and above saturation. The parameter of interest is the component of magnetization along the field direction, sin, which we define as m. The equation of motion is then expressed. 2 kilometers plus 2 km, 1 minus 2m2 equals mh. D. Numerical solutions are shown at the right for 3 values of the ratio of uniaxial to cubic anisotropy constants, Q/K.